So, today we will take up discussion on another special electrical machine. This is popularly known as stepper motors or stepping motors. And as it indicates, the motor moves in steps, unlike other machines where the motor invariably rotates. Okay. If you take conventional machines, they are rotating machines. So, this is in actual practice not a rotating machine, it is a stepping machine, okay, moves in steps. And they are definitely not the ones which will give out power, but they give out torque. Because when the things do not rotate, for power you require the torque and speed. So, here you will have at most have the torque or a force and displacement, right. So, it is not a continuous energy conversion device. So, it gives power or torque in pulses, right. Now, you are aware from the basic principles that you can make anything to move in step if you make the magnetic field to move in steps, right. Now, if you make the magnetic field to rotate, you produce a torque which will be affecting rotation. But if you make the magnetic field to move in steps, then you will facilitate the rotor to move in steps to align with the stator field. So, this is the principle. You know a normal bar magnet or even a bar, when it is placed in a magnetic field or in the vicinity of a magnet, it will align with the magnet. Okay. If you move the magnet or move the magnetic field, this bar will align with that magnet or that magnetic field, right. This is the principle. So, obviously, this is nothing very new and there was this is a concept which can be exploited from the original concept of electricity magnetism of physics. Okay. Now, what is so special about it? Why is it is becoming more and more popular, right? Now, today millions of stepper motors are being manufactured for several applications, mainly for low power ranges. They are used for example, if you want to open a valve or a gate of a process to allow more water or a fluid to flow. See, what do? You know, for example, if you want to open your tap, right, to allow more water, you rotate it more number of times. So, a stepper motor can be there which will rotate as many times as you want to see that the relevant amount of fluid is coming out, right. So, in many chemical process industries there are many gates, right, or many valves which are operated. Now, I read few days ago or maybe 2 days ago, in one of the beauty contests, I think the girl was asked which is the biggest invention, right, and she rightly told it was electricity. Okay. So, electricity was considered as the biggest invention. You know, last century was declared as electric century by IEEE. Okay. Now, the point, the reason is the future is going to be more electric and less mechanical, right. So, mechanical components are likely to replace electrical systems. So, you will see more electrics in ships, you will see more electrics in cars, you will see more electrics in aircrafts. The earlier many of the things were mechanical movements. In aircrafts you see lot of movements, you know, you have to move you have to move the wings and tires and you know sometimes the tire do not open up and whatever it is. Okay. Now, there are all, so they are all operated by the so called actuators or servo motors and so on. Therefore, there are many applications where you necessarily do not require rotation, but you require movements, linear or rotational movement in steps. Okay. Therefore, this stepper motor is considered to be a very useful versatile motor which operates which rotates in steps. And how does it rotate in steps? As I told you, you have to somehow affect the magnetic field in the stator to to move in steps, and that is done by having coils which are displaced in geometric displacements in the periphery of the stator, and you go on switching different coils. When you switch different coils, obviously magnetic field will be at different axis. So, the rotor will try to align with that axis and then it moves. Okay. And historically, in fact, this is one very nice book by Steppering Motors and Microprocessor Controls by Takashi Kenjo of Japan. It was published in 1984, okay, and he gives the whole history of the stepping motors. I would advise you to read this in chapter 1, Introduction Historical Review in chapter 1. Okay. And he says, in fact, early history is way back to 1927, where I will read an issue of Journal of IEEE published in 1927 carried an article, The Application of Electricity in Warships, and a part of this article described a 3-phase variable reluctance stepping motor of the above type. So, this was in 1927, and of course, it says there has been some mention in 1920s, okay, and he goes through developments, continuous type of stepping motor development for now nearly a century. So, what has been the factors which are making it to happen today much more than what it was earlier? The factors are the following. Number 1, the better magnets are available today compared to, so more powerful magnets are available, and you can have a more electromagnetic designs possible through better understanding of the structures. Number 3, you can more automation in manufacturing is possible, so you can produce millions of such motors. And the most important one is you can have electronic switches which are typically transistors, which can switch the different coils at a high speed and as per your speed. Okay. Now, this is the very important factor is you can develop a small microprocessor or DSP or microcontroller based control electronic circuit which can switch these transistors. Okay. Now, another factor is the development of microprocessor, microcontroller, development of DSPs. Now, that means you can do lot of programming in the software. So, you can give a command. Okay. So, you can program it in such a way, you can give commands so that the appropriate signals can be generated to switch these devices, right. So, these are the latest development which was not there, okay. Maybe 100 years ago that was handicap. In fact, first one which is mentioned is he did the switching is done manually, okay. So, obviously you know there has been the limitation, and in this incidentally the last he talks about, I thought it is worthwhile for mentioning academic activities. I will read. In the later part of 1950s, intensive research on stepping motors was started in the universities and laboratories of advanced industrial nations. The results of research were published in technical journals and magazines. In the 1970s, 2 international forums were established where specialists from the industrial and academic circles from all over the world gathered to exchange reports and hold discussions. One is the Symposium on Incremental Motion Control Systems and Devices, held annually since 1972 under the chairmanship of Professor B.C. Kuo. You must have heard his name. Kuo is the person who wrote a book on control systems of the University of Illinois at Urbana-Champaign, while the other is the International Conference on Stepping Motors and Devices under the chairmanship of Professor P.J. Lawrenson of University of Leeds. I had mentioned to you earlier, he was one of the original inventors of stepping motors and subsequently reluctant motors. They have been propagating the switched reluctance motors also. Okay. So, the Peter Lawrenson organized 3 conferences in England in 1974, 1976 and 1979. Of course, there have been a few more recently. The stepping motor was also taken up as a subject in the International Conference on a Small Electrical Machines held by the Institution of Electrical Engineers in London 1976. Okay. Incidentally, I happened to attend this conference in 1976 at Savoy Place, London. Okay. And there were papers on stepping motors. I just thought of sensitizing you that the developments which have come about and which is likely to make more impact in several practical applications today. Okay. Now, let us look at what do we mean by the stepper motor. This is more general. Let us go to particular. Okay. Okay, what is the stepper motor? So, this stepper motor is an electromechanical device. What it does is it converts electrical pulses. What you do give is you give pulses, okay, into discrete mechanical movements. So, all you need to know, you need to know both electrical engineering and mechanical engineering to understand this, and electrical engineering involves signal processing, involves microcontrollers, involves electronics, okay, and the electromechanics, right. Now, the point is the shaft of a motor, stepper motor, rotates in discrete steps, increments when electrical command pulses are applied to it in proper sequence. So, you expect if you pass one pulse it moved in certain angle, two pulse certain angle, maybe 100 pulses certain angle. So, you can make it any angle or any number of rotations, or supposing you want it to rotate 2.5 revolutions, you can do it. You say 2 revolutions say 35 degrees, you may be able to do it. So, it is a rotation because you may like to move a screw, right, so many angles, not necessarily in integers, but fractions of a 360 degrees, that is also possible. All okay. So, you can put pulses to produce this, right. Now, this is considered very reliable since there are no contact brushes. This is a one of the most important thing is a brushless motor, no brushes. Okay. All the controls are in the stator, rotor is just a non-contact type. Therefore, life of the motor is simply depend on the life of the bearing, because what is the contact point in a motor is electrical contacts are the brushes and mechanical contacts are the bearings where there is a movement. Okay. Incidentally, in this conference in 1976, there was one person, very elderly gentleman, who wrote a paper on brushes. It was on different type of brushes, carbon brushes and so on. And he brought different type of brushes to demonstrate this. He brought a toothbrush, he brought a shoe polish brush, he brought the brush for carpet cleaning brush. He showed, he was very emphasizing brush is so important. Okay. Now, can you tell me what is a brush? Can you define a brush? Is there any way you can define a brush? Okay, most of you use the brush every day. How do you define a brush? So, the brush is an element which is in contact with a moving part and a stationary part to collect or apply certain elements. Is my definition correct? It is an element which is always in contact with a moving and a stationary part, because brush can be stationary and other can be moving, okay, or brush can be moving, other can be stationary. Why is it used? Either to apply something or collect something, okay. So, that is the definition of brush, right, and we use it quite often, So, the motors responds to digital input pulses. Pulses are not analog, they are all digital pulses, right, of certain amplitude in steps. It is injected, a current is there, okay, and that means it can have open loop control. If I apply one pulse, it moves in x degrees, 2 pulse 2x degrees, 3 pulse 3x degrees, okay. So, it can be open loop. So, like if you put 3 pulses it does not go to 4x degrees, right. So, there could be a fairly ideal linear relation between the number of pulses applied and number of angles rotated. Okay. So, you theta versus number of pulses n can be made ideally linear. Okay. So, that means the motor is supposed to be simpler and less costly to control, right. So, that is one of the features that are claimed for this motor. Okay. Now, but there is a problem, because there can also be resonance. I hope you know what is resonance. What is resonance? What is resonance? When something resonates means your response is in tune with the impulse. See, when the voltage and current are resonating, at that condition current is in phase with the voltage, resonance. Okay. And it may give to perpetual oscillations, many resonant condition, and it happens because of the energy storage devices exchanging energy between one type of element to other type of element. If an L and C or a spring or inertia or mass or spring, you can create a perpetual oscillatory motions, and that is possible here because they all exist here. In a mechanical system there is a mass, there is a spring. Okay. So, there all will be, so it might lead to, in electrical circuits also there may be energy exchanges. Therefore, resonance can occur, there are some conditions of resonance which happens, right. And it is difficult to run at very high speeds. Okay. It may slip off, right. You can move in slow steps, but if you increase the frequency of switching to very large value, it may be difficult to sustain. It may fall out of step. Okay. Now, let us go into the features of stepper motors, right. Now, these are features means definitions. Okay. One thing is, we define what is known as a step angle. Okay. Before I forget, I also want you to read the earliest article by Anthony Biancoli, I think is Radio Corporation of America, stepper motor application selection. This is earliest, this was published in 1970 IEEE Spectrum. Okay. And I think it is a very nicely written article. For a beginner, he should read this article first and read anything else. Okay. So, this is a earlier 1970, we thought it was a good article on this area. Okay. In fact, if for your reference, maybe I can write it here. This is IEEE Spectrum. This is by Anthony Biancoli. This is in that is December 1970, page 25 to 29. Okay. And it is called stepper motors. Okay. This is the article, I suggest you read this. Okay. I think you can easily download and read the things. Okay. Now, the features are, a stepper motor rotates through a fixed angle for each pulse, and the rated value of this angle is called the step angle, right. How much angle it will move in a pulse when you give a pulse. And there is also step number, that is number of steps per revolution. Okay. How many steps it will move per revolution is the step number. And it is easy to note that relation between the step angle and the step number S. Okay. So, if theta is the step angle, right, then you can easily see that S here will be 360 by theta S, right. that will be the. So, if it is 12 steps means it is 12 number means 30 degrees for each pulse, right. And it is very clear, if your number of steps are small, smaller the step angle, the higher resolution of positioning. Your resolution is better. I mean, I think you know about resolutions. Okay. So, if anything which will meet you, which will measure 1 meter, so resolution is bad. If anything which will measure 1 centimeter, it is better. So, smaller it is better for the measurement. So, you can go, accuracy will increase. Okay. So, that is important, smaller the step angle. So, it will be better you go for, if you want a more accurate fine tuning, you go to smaller this thing. Okay, high positioning accuracy, that means stepper motors are designed so that they can rotate through predetermined steps angle in response to a pulse signal and come to rest at a precise position. Okay. So, it should, supposing it in a position x, you pass a pulse, you expect it to move to a position x plus delta x, where delta x is the step this thing. Okay. Therefore, your accuracy of positioning is important. It should not go to, you want it to go to maybe 20 degrees, it should not go to 22, it should not go to 22 degrees, right. Then it is not a, it has introduced error, it does not give you this. Okay. So, determine the quality of the stepper motor. So, how good the stepper motor is decided by the accuracy of this positioning performance, right. Now, high restoring torque is produced when a displace from rest position occurs due to a load torque. Okay. After all, you know, it is not that it is operating, there is also a load on the, invariably a motor will be operating something. Okay. So, that acts as a load, and that load can have inertia as well as the friction. Okay. So, there will, it will also produce a restoring torque. Okay. From displacement rest due to the, because of the load torque. Okay. And of course, the most of the machines you would like to minimize the air gap. Why? Why do you want to keep the air gap small? Why can't it be big air gap? Because it will give less flux. If the air gap is more, means larger reluctance, so less flux means less torque, right. Therefore, for the same MMF or a current which you can inject in the stator, you would like to have a good torque, that is right. Okay. The position accuracy depends on the machine characteristics, right. So, how accurate it is depends upon the machine characteristics and also the driving circuit. What is the circuit you are using, right? How, what will be the response of that circuit? Because after all, what you, in a circuit you pass a, normally you pass a voltage which will cause a current in the coils. So, that all these circuits parameters, that means you will notice that the stepper motor invariably does not work on steady state, it always works on a dynamic situation, electrical dynamics, mechanical dynamics, right. There is, isn't it, this is electrical dynamics. What is electrical dynamics? That it decides the electrical, perform the electrical circuits, starting from your source to your electronic circuits feeding into the coils. So, that is the electrical system. There is also a mechanical dynamics. What is the mechanical dynamics? It develops a torque, right, and that causes motion opposed by friction, opposed by inertia, right. So, that is the mechanical dynamics. So, the movement, that means you are interested what this will decide the current response, it will decide the theta response, is not it. Okay. So, this is important in your studies. Now, there is a always, you know, in engineering systems, I always say they do not behave as you want them to behave, there will always be errors. There could be step position error is defined as the largest positive or negative angular position error, okay, compared with the rated step angle. Okay. So, if you say it has to move 22 degrees, it moves 21.5 degrees, there is an error. Okay. So, which can occur when the rotor moves from one rest position to the next rest position. The motor moves from one rest position. So, after all it is dynamic, initially it is in one rest position, it is aligned with one magnetic axis. You shift the magnetic axis, it will move, it is a dynamic situation, okay. But it may move you know, to the new position, or it may have a slight error in the new position due to mechanical or electrical inaccuracies or even fabrication mistakes. Okay. So, the positional accuracy defined as the largest angular position error of a rest position related to the whole multiple of the rated step angle, okay, which can occur during a full revolution of rotor when moving from a reference rest position. So, you wanted to take a position, okay, and that accuracy is defined by the, you know, is related to the error, angular position error of a rest position related to the whole multiple of this. Okay. These are some of the definitions which they use. Okay. And what is the stepping rate? Another definition is stepping rate is number of steps per second used to indicate the speed or in hertz. Okay. So, how many steps per second? Like a frequency is revolutions cycles per second, steps per second is stepping rate, and then the pulse frequency is number of pulses applied to the logic sequencer, which is same as the stepping rate, right. Pulse frequency and stepping rate. See, pulse frequency may be what you feed to the it may be low power side feed to the base drive circuits. Okay. Then stepping rate will be same thing, will switch with, you know, that, you know, after all you put this signal here and then this works as a switch, is not it. So, only when the current, when this current you can call base current or whatever is injected. So, if you pass some pulse here, so this goes into some circuit, okay, whatever, right. Now, you know, this leads to a pulse, is not it, that is this voltage, and of course, it does not mean that you get the same current. So, current may just be something like this, right. I mean, I hope you know this, right. You just pass a small pulse here, then this will result in this one. Okay. I use terms like amplification, whatever it is, etc. Okay. And when disconnect also, so you know that, you know, in a disconnect it may be a freewheeling and then it will take some time. Okay. So, relation between rotational speed, how much speed it will rotate, and stepping rate is given by this formula. If this is RPM, n is in RPM, okay, then the f is the frequency, that is the stepping rate, and this is the step number. Okay. So, if you say f is 50, so maybe s is 100, what will be n? The rotation will be 60 into 50 by 100, that will be 30 RPM. Okay. Now, there is what is sorry okay. Now, there is what is known as a holding torque. Supposing you fix it to some position, and how much torque you can put on that one. Supposing you have passed a current in the stator and rotor is aligns with that, but you go on putting the torque, okay. Maybe put a weight 1 gram, 2 gram, 3 gram, 1 kg, 2 kg, 3 kg, right. Know that you can't put an infinite amount of weight on it, right. So, torque to the shaft after when it is excited, when the motor is excited, then it should not go out of the rest position, isn't it? It may slip off. Torque you can have, is it clear? So, when you excite the motor, it comes to certain given position, then you can go on putting some torque on it, and it can go to certain value beyond which it will slip off. Okay. So, that is the holding torque. So, it can hold up to that torque. Okay. And the larger the holding torque, then smaller will be the position error due to load, okay. Right. If there is a load change, there will be minor error. So, it is all mechanical logic. Okay. Then there is one is a return torque, okay. When it is return position is when it is unexcited, okay. Do not excite it at all, and this will be in permanent magnets. Suppose rotor has a permanent magnet, okay. I mean both, if it is just iron piece is a dead machine, but with a permanent magnet it is not a dead machine because flux is always produced, right. And the permanent magnet machine is there, and you put the stator unexcited, okay, without causing, then what it is the static torque that can be applied to the shaft without causing any rotation. Okay. Even this is also important, this is called rest torque or whatever it is, static torque or return torque. In the return torque, okay, only in PM machines. Okay. So, you have what is known as a return torque, you have another is a holding torque. Okay. Then rest position or equilibrium position, that is the position at which an excited motor comes to rest at no load. Rest position is if we excited if the excited machine no load is there and it comes to that position, the equilibrium position, and then the return position is the position at which a motor having PM in its rotor and stator comes to rest without excitation. That means that is the position it will occupy a PM stepper when you do not put any pulses in the stator. Okay. Now, what are the types of stepper motors? We will name. These are some definitions. One type is called a variable reluctance stepper motor. Variable reluctance means your stator you have the windings and the rotor you have a variable reluctance. Okay. This is a bar, not X. Okay. We will see what is known as single stack and multi stack. Single stack is in the shaft axis, you can have 1 stack, 2 stack, 3 stack, right. So, whatever is there, these are all creating this north pole, south, okay, different poles. Now, by switching different thing, this is going to move, is not it? Switching different coils is going to move. Now, what they do is in the other axis you have stack 1, stack 2, stack 3 in the shaft axis. Okay. Then you twist the shaft 2 will have a different positions than stack 1, right. So, the rotor will align, you can excite one first, then two first, two next, like that. So, there is another variants of control possible because of the multi-stack. Okay. Then there is the permanent magnet step, this is all variable reluctance. Rotor has a variable reluctance and the permanent magnet stepper motor. So, instead of this you have a magnet, that is north pole, south pole is there, right. I hope there is no need for further explanation. And there is a hybrid is what? Combination of those. It can be, you can have magnet, you cut the magnet also. So, you can create variable reluctance. So, these are the various options that you have. Okay. Then hybrid stepping motors have PM in stator. Okay. Hybrid stepping motors, they have permanent magnet in stator. Okay. And there are PM motor, there is also one variety, PM motor with claw poles, poles are held by like a claw pole, that is what one of the. Then there is the outer rotor stepping motor, that means your rotor part is outer, like a ceiling fan. Ceiling fan rotating part is outside, not inside. Are you sure? Isn't it? So, this outer, there is another variety, and then you have linear stepping motors. Okay. Linear stepping motor, it moves linearly, right. Then even among linear, there is the variable reluctance, there is a permanent magnet, right. I hope linear rotation, I hope you are aware what is linear motor, what is a rotational motor. Okay. Is it clear? The classifications that we have. Now, this is the variable reluctance stepper motor. Here stator and rotor are of laminated or solid silicon steel, it can be laminated or solid silicon steel, both stator and rotor. Okay. And generally stator and rotor are of tooth structure, both have tooths. Okay. Tooth means it will have slot also, you can have only tooth, you can't have only tooth or only slot, is not it? Can you? Huh? So, you require tooth as well as slot, right. So, you have the tooth here, you have a slot here, right. So, now step motions as switching sequence proceeds in a, let us say 3 phase, you have 3 phase, that means there are 6 poles in the stator. So, it is basically you can say 6 by 4 in this case, right. Now, phase 1 if it is excited, so the magnetic field is like this. So, it is aligned with this position. So, S1 is on, okay. The phase 1 is on. Okay. Now, what you do is you put phase 2 on, this phase 1 on, this is phase 1, okay. This is phase 2, this phase 1 and this phase 2. So, when phase 2 is on, what will happen? This will move towards, which one will move? You see this dot has moved here. So, there is a movement is in this anti-clockwise direction. It is moved up to this step angle, right, and this step angle will be the difference between the axis angles. I think you can easily find out what is the angle, right. Now, you put after phase 2 you put phase 3 here, if you excite this, switch 3 is on, then what will happen? Then it will this will come like this, is not it. So, this dot, this point has come here, okay. So, it has moved. Now, you please understand that whenever you switch from one to another is experiencing a torque, the rotor is experiencing a torque. When they have already come to the final position, it will not experience a torque. So, where will be the maximum torque? Maximum torque will be somewhere in between. You may say it is almost like the torque versus angle, it will vary in some degrees, right. And this one, and if you again go back, then it has come to this position, right. So, you have a way in which, is it clear?
How is it different from variable?
Yeah, here you variable reluctance you normally go for high frequency switching, there you require a continuous rotation and producing a torque. Here you are happy if it just moves and keeps quiet, right. So, it is movement is in steps and low speeds and low frequencies, okay. That is, and it is a low power. Basically a switch reluctance motor is a big stepper motor, right, carrying big currents, big voltages, big circuits, big torques and big power and continuous rotation, okay. Here everything is small, right, and here it is only for movement like valve control or opening the gate, so, or something like that, okay. Now, there is a VR stepper motor, this is single stack. See, this is a variable reluctance is there, okay, and then single stack. You can see here is also made a claw here, there is a pole here, right, and the tooth here, okay. So, there are, this is one stack, single stack. So, as you go on exciting different coils in sequence, there will be a movement as we have indicated, right, is not it? You put phase 1 and then you can have more number of teeth here. Can you see here? You can, as they say, castellated etc. Okay. Yesterday we said. So, you can also cut the tooth, cut the poles here, right, you have cut it into 2 poles, So, this is also another way. So, you can make it subsequently the angle of movement can be made as small as possible, right. Have you seen the difference? It is not a solid one pole like that, it is a one pole cut into more, okay. So, now the step angle in this case theta s will be 360 by s, or s is the steps per revolution, okay. If there are number of m is a number of phases and n are the rotor teeth per pole. So, you will have this will have a bearing, number of phases, if more number of phases angle is less, if more number of tooth per per pole, then it will be further divided by this 360 by m into nr, okay. Now, this is one variable reluctance stepper motor multi-stack, right. Have you understood what is this multi-stack? So, this is stack 1, this is stack 2, this is stack 3. Now, there is an angle between this rotor stack here, okay, and this stack here and this stack here. So, if you excite this first, you can excite this with one phase. So, this can be only one coil. So, this will align with this position. Next you excite it, it will move to that coil, because this stack is different. You see there is so either you make a skew between the rotor or make a skew between the stator, either way it is okay. Skewing is shift the axis, there is the axial shift of this tooth and the slot between stacks, right. So, you have this. Now, afterwards you excite this, so this will move, right. So, the shaft gets a torque experienced by successively varying. So, you can, so here there are only 3 coils now. Multi-stack means there are not multiple coils in each stack, have you understood? There is only one coil in each stack. So, it energizes the poles. So, it creates the poles in the stator and respective rotor gets aligned, then it creates the poles in the rotor, respective rotor get aligned, then this. So, if 1, 2 or 3 stator is magnetized at one time, okay.
These are not a rotor.
Which is stator? No, this is the stator, this is the rotor, okay. This is the stator, this is the rotor, this is the stator, this is the rotor, okay. I mean, but the rotor is on the same shaft, but the different stacks it may be skewed, okay. There is an angle between the axis. So, each phase in this is one stack, there is only one coil, this phase winding, you pass a current through this and come out of this. So, it goes on magnetizing all these ones, is not it, in appropriate way, okay. So, then it has aligned, all these are aligned, Now, in this case the stator and rotor poles will be same. See, number of stator poles will be same and number of rotor poles. Is it clear? Okay. But there is only one coil here, which will magnetize all the ones. It is not that only one of pair of poles are magnetized. Okay. So, this is a different, this is called multi-stack. Okay. Then in PM stepping motor, okay, I think this is as a tin can or a can stock motor. Rotor will not have teeth. You can have a, this is PM, right. You can put phase 1, this will get aligned, phase 2 it will come here. Okay. So, there is a, then you can continue, either you can make a rotor will not have teeth as with the VR motor, instead a cylindrical PM. So, no teeth in the rotor. Okay. So, you can have, you can excite 1, 2, 3, 4 makes the motor rotate in 90 degrees. So, you can have 1 here, then 2, then 3 and 4. So, you can excite like this. Okay. So, when one is excited, other 3 are unexcited. So, it will move. I think this is very simple. So, a polarized rotor poles provide an increased magnetic flux density, and because of this the PM motor exhibits better torque, okay, than a VR motor. The feature of PM motor is it comes to rest at a fixed position even if excitation ceases. See, even if there is no excitation, it comes to certain position called the it is called a detente or rest mechanism. Okay. Okay, the problem of PM motor is that magnets are costly, and maximum flux density is limited by the magnetic remnants of the magnet. I hope you know what is, in a BH curve your permanent magnet operates here, okay, BH curve, this is BH, right. Now, how much it can, these are critical, this is the maximum B and this is maximum H minus, right. So, remnant flux is decided. So, that is what limits the operation of the PM machines. Okay. Hybrid, of course, hybrid stepper motor is more expensive than the PM stepper motor, but provides better performance, okay, with is a combination of these two, it is the advantage disadvantage of both together. Okay. So, with respect to step resolution, torque and speed, hybrid stepper motor combines the best features of PM and VR, okay, but it is expensive because you have to make the magnet and cut it also. Okay. A rotor is multi-tooth like VR motor and contains an axially magnetized concentric magnet around its shaft. Okay. This increases the detente torque, holding torque and dynamic torque characteristics of motor compared to each of the things. So, these torque levels are higher in hybrid machines. Okay. This hybrid motor, so you will see this is the variable reluctance and there is a PM also. Okay. This is, okay, you can have this is a hybrid machine, right. Then the hybrid machine stator is like a VR motor. So, you look at the stator, there are variable reluctance implying, bifailure means winding in 2 parts windings for bipolar excitation. Bipolar excitation, here you can, unlike in SRM, you can have a negative current also, okay, right. So, this is one of the features. Okay. A rotor in its core has PM providing unipolar excitation lengthwise. Now, this is also you can see your axial, you can produce the flux in whichever, you see these are the north pole, this is the south pole. So, the flux levels can be changed, that means unipolar. Okay. So, I think a minute, right. This is each end of the rotor situated on the core is covered with tooth soft steel. Now, this is also one of the thing, you can put the magnet below and put a variable reluctance. You can have a laminated steel, you have a PM here, you understood, there is a permanent magnet inside and covered with tooth soft steel outside, okay, and that is tooth. So, you can see that this creates new type of configurations, because nowadays there are a lot of finite elements tools available in which you can study, make this geometry, etc. Okay. So, we will stop it here and we will take up in the next lecture. Okay.